Someone in the comments will point to a Mathematica script that would create and solve these. That'd be fun to see. So I've collected all the components of the Ricci tensor on the left. The top two, I showed the derivation, and the bottom two, the r theta theta and r phi phi, I didn't. What's apparent from all of them is that the spatial components all have a factor of an a double dot a plus 2a dot squared plus 2k. This is multiplied by the corresponding spatial metric grr or g theta theta or g phi phi. We just need to divide out the a squared to get the Ricci tensor for each one. All three space-based components for the Ricci tensor can be summarized on the right, r sub ii. G sub ii is one of the spatial metric components. The time-time component of the Ricci tensor sits all alone at the top. Our next object that we now need to construct is the Ricci scalar, r. To do so, we need the raised index versions of the metric, and we need to contract the Ricci scalar by summing over all the alphas and betas you see there. Right now, I really want to emphasize that this Ricci scalar r is exactly not the same as the radius of curvature in the metric. It is just an extremely unfortunate turn of events that Riemann and Ricci both begin with r, and r is often used to show a radius for spheres and circles and such. Please don't worry about it, it'll be fine. If we sum up the products of the metric and the Ricci tensor for all four combinations, we get the expression in yellow at the bottom for the Ricci scalar. It's now interesting to note that we've just hemmed in the units for the curvature constant K. The scale factor A might be unitless or have units of length depending on your metric's definition. No matter what they are, they would cancel out. But there are two time derivatives in there. To match the units, K must have units of inverse time squared. But remember at the beginning we set c equal to 1? That means we should geometrize it and call it inverse length squared. The curvature constant has units of something per area. What that something is might not end up mattering. What is important is that the K contains the nature and size of the curvature in whatever isotropic, homogeneous, and uniform spacetime we choose. Okay, let's file the Ricci tensor and scalar away for a moment to address a needed clarification from the textbook. Dr. Ryden uses a mostly non-standard coordinate configuration for her version of the Friedmann-Lemaître-Robertson-Walker metric. She uses throughout the text an altered version of the standard hyperspherical coordinates. The good thing about using either form you see here is that the radial component is almost a distance. It's a co-moving coordinate distance specifically, but it's much more like a distance from the origin than the reduced circumference coordinates, which is actually not based fundamentally on a distance from a central point in the coordinate system. The upshot is that dr is very much like a little change in the co-moving radial direction than the previous metric. Since Ryden will show us a lot of things that relate to distance very soon, this particular coordinate choice makes the results we'll get easier to read and interpret. On the bottom is the real and true version of the standard hyperspherical coordinates where the curvature constant K is a real valued number that can be positive or negative. It incorporates both the size and nature of the constant uniform curvature, one number to rule them all, and so forth. But Ryden takes a different turn. She implicitly uses the gnarly analytic function that we saw before and fishes out the two parts of the curvature constant K, the size and the sign. She labels the three types of universe, closed, flat, and open, as kappa being +1, 0, or -1. This is pretty nice because it follows our intuition about the three different types of uniform curvature. It also helps in a later argument about how one type of universe cannot become another. We'll talk more about that in our toy universes chapters later. Ryden also pulls out the radius of curvature into r sub 0, making it into a ratio with the co-moving radial coordinate. This looks neat and helps to remind us that there's no units on an argument for a sine or a hyperbolic sine function. With the curvature scale size, r sub 0, out in front, we can kind of intuit an amplification of the radial curvature from the functions. On the top, the positively curved space curves back onto itself at a co-moving distance r0. The open universe's negative curvature leads to an exponential growth on the scale of the co-moving radial coordinate. The kappas serve to restrict our thinking to one of the three choices. The link between the two equivalent flavors of this metric is shown on the right. The curvature constant K is just kappa over r0 squared. This is obvious by comparing the two triplets. Using this form of the metric, we're going to repeat what we did before. Just to not drive myself bonkers, I've flopped back over to using the S sub k form of the hyperspherical coordinates rather than the S sub kappa. It works out to be exactly the same thing in the end. First, we note the metric itself across the top. We're going to follow Ryden's example and leave in all the constants like c, g, the Boltzmann constant, and the Planck constant. This is an introductory course, so there's really no reason to add the confusion by using the elegant Planck unit abstraction. We can always set them to 1 to make it elegant later. With that, we see the metric's tensorial components over on the left. As expected, there are 4 of them with no cross-product terms, and then we take the partial derivatives of each of these metric components with respect to each of the coordinates and keep only the non-zero results. We've now got something that kinda starts to look nasty there, a partial derivative with respect to radial coordinates of the S sub k function. That's going to give us a wallop of a headache in just a moment. One big change is that we do not see the curvature constant K anywhere except as a naughty little subscript. It's buried inside that S sub k function. Right now, we don't want to evaluate the partial derivative of that thing. We'll get to it shortly. Next, we use all those partial derivatives to construct our Christoffel symbols. These look different from before, again with the addition of c for the speed of light, and the S sub k and their partials floating about. Near the bottom, in addition to the product of S sub k with its differential, we're now even seeing the ratio of the partial to the actual S sub k function. At this point, doing that algebra would make even the geekiest mathophile wheeze. We'll leave it in this form and hope the juice is worth the squeeze when we evaluate it later. Now for your edification, I wrote out all the partial derivatives for all the Christoffel symbols, rather than obfuscate and prestidigitate like I did before. This time, no dodging. This is truly ugly stuff, and there's a lot of it. We've got squares of partial k's, we've now even got second partial derivatives of S sub k, and worse, multiplied by S sub k. I really have no idea what that function would look like analytically, or even if there's a good way to express it other than what I'm doing here. Given this higgledy-piggledy conflagration of scale factors, c's, and various trigonometric thingies, it seems wild to hope that this will somehow sort itself out into a simple and rational form. For the Ricci tensors, I'm really not going to go through all the paperwork and image creation on my slides. I'll just pass that up and show you the end result. When we combine and sum all the appropriate Christoffel symbols and their derivatives, we actually do get these components below. I really do encourage you to try it out. You can use my video as a check on your progress to see if you got it right. You might as well try it. You're this far along in a proper introductory cosmology course, and if you were sitting in my class, I would make you do it as homework. So, chop chop. What's interesting about all these forms of the Ricci tensor is that it's really not far off from the other metrics component tensors at this point. We have a bunch of partial derivatives of the S sub k function and some ratios of them. Since the space is the same, and even though the coordinate choice is different, we should expect the Ricci tensor to be very much the same as before. Somehow, it should work out. You can see that there are only 2 different terms involving S sub k to evaluate. A second partial of S sub k over S sub k, and 1 minus partial S sub k squared over S sub k squared. Let's see what they work out to be. To evaluate both terms, let's please not use the analytic function and just evaluate the equivalent triplets. Since we're back to the standard hyperspherical coordinates, I'm going to evaluate them in turn. For each of the real valued ranges of k, we have 3 functions S sub k. The second line is each partial derivative, and the third line is the second partial derivative. Using the definitions of sine, cosine, and their hyperbolic equivalents, we find that all 3 regions of k have the same result for these 2 expressions from the Ricci tensor. That's some dark academic magic I implore you to replicate on your own. You'll be pleasantly pleased with yourself for winning it. Now let's plug these results back into our Ricci tensor components to see what we get.